Hello, everyone. Today's lecture is online and virtual, and that is because I'm giving a talk at a conference in Bonn, and so I cannot be here in person. We left off last time on the topic of cross-validation. The aim of that cross-validation was to bring in more randomization into the training process. The idea being that you partition your entire data set into, so the training and test, the training and validation data set, one should say, into, in different runs during your learning. You will have, let's say, this subset of data for validation and this for training. In the second run, you will do it slightly differently. And so you will split the data into n folds, and distinguish, and bring in more randomization. The idea being that you're more robust to how the partitioning into train and test is done so that you're less prone to any kind of errors there. And in principle, this technique becomes very important when you have limited training data. But as I mentioned last time, when you have very large models, you typically always have limited training data. And that is, in very many real world big learning challenges, is the key bottleneck, that ground truth labeled training data is hard to get, especially if you need millions of it. And so then this cross-validation technique comes in very handy to improve the training and learning. And as always, you would, use training and validation data to find your hyperparameters. This is, the number of layers in your network, the number of neurons in each layer, the type of network architecture, whether it's a convnet, a resnet, a transformer, or whatever it might be. We'll have more about that later on in class. But also the learning rate, for example. What you can expect then is the following, the ground truth that you get for training a supervised learning problem is never perfect, right? Why? Because either it's humans who label things, average humans, and then, if your classifier is supposed to distinguish the different kinds of dog breeds, and then you ask someone like me who has little experience on different dog breeds, my labeling will not be perfect. And so the ground truth you get from people like me will not be perfect either. Or in a medical case, if you ask 5 different radiologists, people say you tend to get 7 different answers, right? And so you can expect there will be some error in what comes back as the ground truth, right? And let's say that is 1% error. Then typically you can expect when you train a neural network, the training error will be above the ground truth error typically, right? There are cases where we can achieve better than the ground truth, but typically we would expect that the training error is higher. So let's say 5%. And then there is a validation error, the question being how well does it generalize from the training error? And that is typically also higher than the training error. But the key challenge is you want to bound the growth in error, right? You want the test error to be small, to be ideally in the range of the ground truth. You want your network, once you deploy it, to be on par, ideally, or close to what experts can do, let's say, in a medical setting, right? And so the challenges are twofold here. Once you want to reduce the bias, you don't want to do underfitting, right? You want to make sure, for example, that your network capacity is sufficiently large to explain the training data to really be able to get good results on the training set. But at the same time, you don't want to overfit, so you want to keep the variance at bay. You don't want to overfit so that the test error is ideally also small. And this is often a compromise, and this is what's called a bias variance dilemma, that you want to have, the network capacity and the amount of training data on a level where both the training error is small, but also the validation error doesn't grow too high. And so there are different ways you can look at this. This is from Andrew Ng. You can look at how high is the training error. If the training error is high initially, it might well be. And then it shows you that maybe your model is not suitable, that you might need a bigger model with more layers, more neurons, or maybe a new model architecture with different connections, right? Or you might just simply need to train longer with a better learning rate and a learning scheme, like we discussed, right? And then once the training error is sufficiently low, then you will check what is the validation error. Here it's called train dev error. Why is that? That's because sometimes the validation set is called the development set in some literature. And so then the validation error is what's called the train dev, or the transfer from train to dev. If that is high, then you might need more data, you might need regularization. And if the validation error is high, then you might need new model architectures to consider. And so this is the scheme that you can pursue to get to make sure that you end up with a good model that ends up having a good test error. But as I mentioned, you should never use the test error in the development, right? So that should only be used to finally confirm that your method works. So in general, you don't want to underfit, like on the left, where you have a model capacity, it's a straight line, or in multiple dimensions, a hyperplane. That is often not sufficient to separate, let's say, as in this case, the blue and the red class. If your model capacity is too high, you can separate all the training data. You get zero training error. That is typically suspicious if you get zero training error. And then what you can expect with an overfitting model is that it will not generalize well to the validation set and the test set. And so what you really aim for is an appropriate model capacity and appropriate amount of training data that will give you a good model that generalizes well. The key challenge in real-world learning is that you cannot plot this like you do here, because you're typically not working on a two-dimensional classification problem. This is what people looked at, let's say, in machine learning in the 70s and 80s. But now, if we want to train models that have hundreds, thousands, of possibly even millions of parameters, we can no longer visualize the curves and decide by visual inspection on the hyperplane whether it's appropriate or not, right? What we can do, and that is what I highly recommend, is plot the training development, right? The training, and so plot your curves, the learning curves, right? That tell you how does the training error develop, let's say, as a function of time or as a function of the model capacity here. And then you can expect that if the model capacity is sufficiently high, the training error keeps on going down. But at some point of model capacity, the generalization error will go up again, right? The validation error will go up because we're in the overfitting regime. And so you don't want to get into the overfitting regime, and you want to get to that sweet spot where you have a good generalization error, where the generalization or the validation error is low. And how to find that sweet spot is an important challenge in training a neural network. And what I recommended, that even during training, you immediately plot the learning curves. You can plot the accuracy, right? And you can plot the loss over time of training, for example, right? And the different tools that you have at hand, for example, TensorBoard is a tool that's used by many. They offer this functionality that you can plot all these curves, and I recommend highly, and we'll talk a little bit more about that now, to plot these curves to make sure that your learning is progressing well, right? And this TensorBoard can be used by several softwares, libraries. For example, it can be used by PyTorch, also by TensorFlow. In this class, we're mostly using PyTorch. But if you want to use TensorFlow, you can also use the TensorBoard for that, obviously. What's important with these curves is the actual numbers that you see on the left. They don't typically matter because this, if you rescale your loss function by factors or you have a constant offset, then you would see that in these numbers, right? But what typically matters is the development of these curves, how they decay over time, and that's what you want to look at, right? And what you see in these curves typically is the average loss over a mini batch that is shown in dark green, and light green is kind of the loss on the current samples, and that will oscillate a little bit more around the dark green curve. And so these losses look reasonable, but you should not just consider the training loss, but also the validation loss, of course, right? Here is some examples. On the left, for example, you see a training as a function of epoch, the loss as a function of epoch. And what you see here is the training error in blue and the validation error in green. And there's two things that are a little bit disconcerting, and that is, first of all, the training loss and the validation loss, they go down, but with essentially linear slope over hundreds of epochs, right? So you're putting a lot of learning into it, and it's decaying at a constant rate. And that's typically not what you would expect. You would expect a faster drop off initially and then a slower decay later on. So this linear decay typically indicates that there's probably, that your learning rate is probably too small and you might try to go with a larger learning rate, right? Whereas the plot on the right, uh, um, you see that both the train and validation error drop very fast initially, but then, the curves become fairly flat, which is also not desirable, right? Right. So as you see here, after 3 epochs, it's essentially flat and there's nothing happening somehow. And that indicates that maybe you're oscillating around a minimum and maybe the learning rate is too large to further converge to the desired solution. The other thing to note on the right-hand side, you see it that the validation error starts much lower than the training error. This is usual because typically you do a few rounds of training iteration before you validate. And so by the time you compute the validation error, you've already much better, network parameters. Overall, these curves are fairly reasonable though. So, apart from showing that maybe the learning rate could be a bit adjusted, overall this is is decent, let's say, curves. These curves here are a little bit troublesome. So on the left, for example, someone trained for 100 epochs, right? Even though the validation error went up after 20 epochs already. So that kind of shows you don't need to continue. We're talking, sometimes this can be hours that we're talking about. So you trained a model for hours and it's clearly in the overfitting regime after 20 epochs of learning, right? And so this kind of indicates that the capacity is too big because it's overfitting. So maybe you have too many layers, too many neurons in each layer, etc. Or that that you don't have enough training data, or that, for example, the regularization on the network weights is too weak. On the right-hand side, you have weird training curves where you clearly see massive oscillations, right? And that typically indicates that your learning rate is too high. And then once the error goes up, then, maybe you're even diverging, right? The other thing you see is that there is clearly overfitting happening around 100. So there is a big gap and the validation error starts going up again. So this is, so these are curves, but you can interpret them, you can visualize them, and that will help you to find suitable learning rates and suitable network architectures to make things work. Here's two more examples of training and learning curves. So train and validation curves. On the left-hand side, you see that the first thing to observe is that the decay is too slow at the beginning. And typically you would like to see these kind of exponentially decaying losses, but here, it begins too slow and then it seems to go faster later on. And so this indicates that possibly you might need a larger capacity or a higher learning rate to get moving faster, right? In both curves, you see that the validation error is actually lower than the training error. That should really not happen in practice, right? This doesn't really make sense that the network does better on the validation set than it does on the set it trained on. So that indicates that potentially there is some bug in your code. So, as I said, the validation error is usually above the training error. So to summarize, you don't want to have underfitting and you don't want to have overfitting. So underfitting being that training and validation losses decrease even at the end of training. That means you're underfitting. Overfitting means the training loss decreases, but the validation loss starts to increase. So you don't want to get into that regime either. And ideally, you want to have a small gap between training and validation loss, and both should go down at roughly the same rate. And ideally decay in this kind of exponential way without too much fluctuation. And overfitting maybe one point doesn't necessarily mean that the validation loss increases, but it just means that you have a massive gap between the train error and the test error, the validation error. Let's say here, for example, on the right-hand side, right, the validation error doesn't increase, but it's just very far from what the training error is, and this is what you should kind of avoid. So overfitting means that the training error is just much better than the validation error, and that shows that something is kind of fishy in terms of the generalization capacity. A bit more, what signs to pay attention to when you train a neural network, when you plot the learning curves. Um, so the first thing is if the training error does not go down, that's obviously not good. That's the first thing you want to assure, that the training error goes down. So that requires sufficiently large network capacity and a sufficiently, suitable training learning rate, not too large, not too small. The next thing, if the training error does go down, you want to make sure that the validation error also goes down so that you have a generalization, that the network generalizes, that you're not overfitting, etc. And then the thing to also pay attention to, if the performance on the validation set is better than on the training set, that really indicates that something is fishy and that you might have a bug in your code. Another thing you can look into is whether the tests on the train set are different than during training. So if in the validation, the tests on the train set are different, then something is off somehow. What's very important is you should never use the test data. I mentioned that before. So this is really bad practice because it's considered cheating, right? You want to develop a method that solves a problem, but if in the development of the method you use the knowledge about what the solution is, then that's very much cheating, right? It's like if you want to have an oracle predict what card it is on a card game, and you have the oracle look at the card and before it generates the prediction, that's obviously cheating. And that's very much what you would do if you were to use the test data in the training or the test data in debugging your algorithm, right? So you should only use that at the very end to confirm that the method works, but not in the development of your method. A bit more on hyperparameters. There are many hyperparameters that you would tune during in the train and validation phase, and that's what you use the validation error for, to tune the hyperparameters of your network. So this is first and foremost the network architecture, the number of layers, the number of neurons in each layer, the number of weights, but also the number of iterations that you use. Then the learning rate parameters, right? So the decay that you implement, and the different, whether you're using atom or some momentum, etc. Then the regularization, this will be covered more in the next lecture, and things like the batch size that you use, the mini batch size, how big is it? Is it suitable, etc.? Is it well tuned to the architecture of your GPU, etc.? And so all of this should be optimized. And for example, the batch size, how can you do that? If the batch size is too small, then the curves fluctuate a lot. We've seen these green curves here, right? If there's a lot of fluctuation here, an oscillation in the decay, it indicates that your batch size is likely too small. And so ideally, you should choose the largest conceivable batch size that is compatible with your GPU architecture. And as we saw that, if you have limited GPU resources and you want a larger batch size, then you can do this technique that we call gradient accumulation, where you basically compute the gradient over mini batches, and then before doing the weight update, you aggregate these gradients over several mini batches, thereby, basically mimicking a larger GPU and a larger batch size, right? And it's kind of a trade-off between runtime and batch size that you can generate there. And this is typically something that you always have in training neural networks and in any kind of machine learning, that you can trade between memory and runtime, right? If your memory is more limited, you have to dedicate more runtime to get the same performance. The usual trade-off between compute and memory. How do we tune the hyperparameters? There are many ways to do this. For example, if we have two parameters, then we can, the learning rate and some other parameter, etc. Then we can use manual search. This is very common to just try different things and see how they work, look at the learning curves, see which works better, and get an intuition whether your learning rate is too large and too small. What people often do is this kind of binary search, where they identify two parameters, or one is too big, one is too small, and then you take the value in between, and if that's still too large, you go again in between the first and second, and that way you can quickly kind of zoom in on the suitable parameters. That is assuming that you have a clear dependency on the choice of the parameter. The next thing you can do is you can do a grid search. And that is, you have two parameters, the first and the second parameter, and you basically split it into a grid, and then you sample the entire grid. You can either do that in a regular grid, and this is called grid search, a for loop over the two parameters, and then you try all of these values and see what works. And you can, have a quantitative loss, for example, the validation error or something, to determine which parameter set is the best, or you can do it in a random search. The random search is very much like grid search, except that you're not fixed on a predefined grid or right. So you have a range and you just sample randomly, let's say, with a uniform distribution. How do you start? And this is a common mistake. Often people want to start big, and this is a general recommendation in all science. When you develop solutions to problems, start with the simplest conceivable instance of the problem, and then validate that this actually works, and then carry it further. So don't take the entire ImageNet data set and throw it in and hope magically it works. Start with a single training sample, right? Let's say one image of a dog, right? And then you want to train a network that, in the case of that dog, says, yes, it is a dog, right? So it's just one. And so ideally, if you have one training sample, the classification error on that one should be 0. It should really classify it as dog. So you really want to overfit to that single sample. And similarly, then you go to, let's say, a handful of samples, say 4 dogs, and see whether these are handled correctly. And ideally, there again, you should have a 0 training error. The network capacity should be large enough to perfectly distinguish the 4 objects, right? Let's say if it's a dog breed classifier, for example. And then you should move to hundreds and thousands of samples once this works. And then ideally you should see some form of generalization happening. And this is kind of the magical moment of neural network learning, and that at some point it generalizes beyond the training data and also starts to work on the validation data. So obviously, for example, if you go to 4 in the second stage, then you should have a model that can, have 4 different classes, right? That allows to distinguish 4 images and classifies them into 4 different classes. So the number of classes has to grow a little bit at each stage. But as I said, in this intermediate stage, the training error should still be 0. So you should still have 100% correctly classified. And you can check how fast it does that, right? So you can validate that you're in that stage, that your model actually works, that the forward pass works, that the backpropeller works to compute the gradients, etc. And even simpler things, you need to check that you can actually load input and output data. Can you load the input images, the training the ground truth labels into your model, and can you overfit to it? That's really what you want to do in that stage. And then you can plot the training curves. You can get a feel for, whether you have the right learning rates and things like that, that the learning curves have the right progression, that things look good. And then once you go to more and more data in the last stage, you should start to see some generalization. Then you should actually start looking at the validation error and should verify that it also goes down, so that you're not fully overfitting to the training data, but also generalizing. And so this is a step-by-step approach, and I always strongly recommend, if you start from scratch, really start small. This may be different if you work, and this is a common thing in our community, that people don't start from scratch learning their own networks, but they start with some pre-trained network. Then things are a little bit different. Then you start out with a network that can also already classify, let's say, all sorts of categories on the ImageNet data set or something like that. How to find a good learning rate? So you use all the training data with a small weight decay. You perform an initial loss check, let's say log C for Softmax with C classes. We'll come back to that a little bit in the next chapter on multi-class classification and different losses. And you want to find a learning rate that makes the loss drop significantly within, let's say, 100 iterations, right? So good learning rates, there's different ones you can try, 10 to the power of -1 to 10 to the power of -4, for example, and see how that works, right? Then you can do a course grid search on a few values of learning rate and weight decay, for example, to see which ones work best. You do it on a course grid to not spend too much time on it, right? And then you should use that to train a few models for a few epochs and choose suitable values for the weight decay, 10 to the -4, 10 to the -5, or 0. Right. And once you've identified suitable values on a course grid, then you can refine the grid. So you do these things in a course to fine manner just to be efficient, right? And you would pick the best models found with a course grid and refine these. So you wouldn't keep all the models in the game, but only those that work best on the course grid before you refine the grid, just to save time, right? And then you would do a refined grid search around these models in the regime of model parameters that you identified on the course grid. And then you would start to train them for longer, let's say 10 or 20 epochs, without learning rate decay. And as I mentioned, the most important tool for all of that is the tool that allows you, like this TensorBoard tool that allows you to study the loss curve so that you see whether you're in reasonable regimes of learning, that both training and validation errors decay in an appropriate manner. What you should always do is you should do timings, right? So you should check how long does each iteration take, right? This forward pass, but also the back propagation, right? How long does it take? Get precise timings. For example, if a single iteration exceeds 500 milliseconds, then things get dicey, right? Because then, if you want to do hundreds or thousands of iterations with different parameters, things get very slow. You don't want to wait forever for the neural network to train, right? This is a common issue in the neural network age, that neural networks can take hours, days, and weeks even to train. And if it's big networks, powerful networks, this is sort of unavoidable, but still you want to make sure that you have the best possible timings to start off with, right? And you should look for bottlenecks. Data loading, for example, maybe you want to load images of smaller resolution to make things faster if that is a bottleneck. So you may want to compress images into something like JPEG, for example, right? But then the question is, what is the bottleneck, right? Is it faster if the loading is an issue, then you want compression. But if then the decompression of the JPEG images, it takes more time than the loading, then you may want to go with raw PNG imagery, right? So that's there are trade-offs there, right? You can compress images very immensely, but then the decompression might take time as well, right? The other thing is you can look into data loading, whether you train from an SSD or from a standard hard drive, and that can actually make a massive difference. So hardware plays a big role, that, training from an SSD might be much faster than from a standard hard drive. And in general, in Python, anything that runs on the CPU, like for loops, for example, that is really slow. And you want to make sure that things run on the GPU, and you want to make sure that there is the least amount of synchronization between GPU and CPU. because this is how, CUDA works. You have this device sync, and it's not always easy to transfer information between GPU and CPU. Uh, um, um, and you need these device syncs because otherwise the CPU does not wait for the GPU output. And there's a lot of intricacies about how the GPU works. You have event timers. These GPU calls are asynchronous, and so any kind of synchronization is an additional effort if you need that. And you want to look at, estimate the total time. How long does it take until you see some pattern? How does it take for the network to converge to the desired solution? Common mistake is that people just, say, oh, let's take a super big network with millions of parameters and let's train it for 2 weeks and then we see where we stand. And typically you might find after 2 weeks that you've picked the wrong data, that, either the data loader wasn't working or um, um, that let's say you had the wrong learning rate and it didn't actually converge. So this is something you should monitor closely, and maybe you shouldn't start with a network with millions of parameters. Right? Because the challenge in the beginning, the aim of all this when you're learning about neural networks is that you want to get hands-on experience. You don't want to necessarily beat the state of the art on the ImageNet classification challenge or something like that, but you want to simply be able to, to get a network that does something reasonable, right? You want to make sure that the data loads correctly. You want to make sure that the forward pass works and doesn't take too much time. You want to make sure that the backprop learning of the gradients works. You want to actually validate that there is a learning at all, that the train error goes down, that the validation error also goes down in a similar fashion. And you want to just get the debug cycles down, right? Ideally 2 minutes, right? So that you quickly identify what the issues is, that you get experience with what can go wrong, what do you have to monitor, what are the parameters that are critical for things to work, right? Because these are fairly complex models that have many parameters, both in the network architectures, but also in the training regime, as we've seen. And I do recommend to learn to, use and train your own neural networks, not just work with off-the-shelf pre-trained networks. Right? A few more recommendations. You see, this chapter is very much about practical recommendations. So use the loss curves for validating, for evaluating the training, the validation, the test curves. The evaluations, they need to be consistent so that the numbers are actually comparable. And also, this is a common recommendation for debugging. Don't change too many things at the same time. So don't say, I added 5 more layers and I doubled the training size and now I also trained 5 days longer and now it's better, right? That's really great. But then you don't really have an understanding of why it is better. What was the aspect that improved things, right? So, neural network learning is a complex system and you want to tune one screw at a time to get a good intuition and understanding about what each of these screws does to the overall system. And you want to understand, and for that, you want to visualize the input, the prediction, and the ground truth, things like that. Common mistakes that when people train neural networks, that they don't start small, they don't overfit to a single batch first, but try to do the whole thing in one go, and that's a common challenge, right? And they forget to, it's a very common thing to forget to toggle between train and evaluation mode for networks so that you don't, do evaluation and you're actually looking at the training set rather than the evaluations, the validation set, right? Things like that. So we'll come back to that later on. And you need to call zero grad to really remove the old gradients. You aggregate gradients in the backprop learning in PyTorch, but in every new run, you want to make sure that you initialize properly, that you don't have the old gradients in there, because that will distort everything, obviously. These are common kind of errors that we see when students implement their first neural network learning. And something else that happens a lot is that, you have to make sure things are consistent. So, for example, that you don't pass a softmax output to a loss function that expends raw logits. Logit, will come to that, is this logarithm of p over 1 minus p that you get there. It's called a logit. A bit more on this tool TensorBoard that we use for visualization performance. There's a number of visualization tools. As I mentioned in this class, we're mostly relying on PyTorch, not TensorFlow, but TensorBoard can be used in both. There's other visualization tools like Wisdom and Neptune, etc., but we find TensorBoard works fairly well. But if you want to use others, that's obviously conceivable. And here's some things you can do. So you can set the smoothing factor. You can plot train and validation in one chart. You can also, as you see here, plot both the accuracy, how well does it solve the task that it's supposed to solve, how well does it classify, but also the loss function. And you can simultaneously plot curves for different runs that you can select on the bottom. And so you can see how did it go in this run and that run, and compare a little bit, maybe, if you use different training parameters, different learning rates, etc. You can also visualize the model predictions themselves. That is, particularly interesting when you train generative models that are supposed to generate images, right? And you want to actually possibly inspect whether the images it generates of a car really look like a car, etc. So you want to see that performance development there qualitatively. You can also visualize confusion matrices showing you, for example, which classes the network still has trouble with. Ideally, they should not confuse the different objects in a classification challenge. But if the matrix isn't really block diagonal like here, then it indicates that possibly something is off, that maybe two classes it has trouble distinguishing, and you can validate that here through these confusion matrices. You can also compare hyperparameters, showing you how different hyperparameters give different results, right? So you can overall track the learning progress. And one should say that good machine learning engineers and developers, they just have very good bookkeeping of what works, overview of the different hyperparameters, learning curves, adapt very quickly, and they have a complete understanding, and this is what you want to reach, that you have an overall picture. Have you, tried changing the number of layers? Have you tried changing the widths of layers, the architecture, the learning rate, the weight decay, all the things that can matter? And what I've found is that often beginners make that mistake. They focus too much, let's say, on one specific or a few specific hyperparameters and tune these for days and weeks, right? Whereas the one hyperparameter that would have really made a difference, they never looked at it, right? And so make sure you've looked at all things of the story to get a complete picture that you haven't forgotten anything. And for this, TensorBoard can be very helpful to visualize everything. That brings me to the next lecture that contains more about training neural networks, about output functions, loss functions, and activation functions. So let me see if I can move over to the next lecture. It's gonna take a second, just a second. And this is lecture 7 on loss functions and activation functions. Just a second to make sure I'm sharing the right screen. Here we go. So this is on loss functions and activation functions. That we'll talk about some more. Short recap, we talked about learning rate, the implications, whether you have a good learning rate, then things decay properly. If the learning rate is too low, like in the blue curve, then you see the loss function decaying, but with this very common linear slope in the beginning, showing you that maybe the learning rate, especially initially, may be too low. If the learning rate is too high, you get a curve like the green one where the loss drops very fast initially, but then things plateau and don't go down further because you're kind of oscillating around the minimum, right? You can imagine, because of the learning rate being too high, the steps being too large. If the learning rate is way too high, then you actually start diverging, and you see that in the loss because the loss doesn't go down, but actually goes up. We also discussed this bias variance dilemma, the fact that you want to get a low training error, so you want to fit the training data, but you don't want to overfit, meaning you don't also want to get a reasonable variance so that it generalizes well. And you want to train on training data in a way that hopefully you get a good generalization to the validation set, and then a good performance in the end on the test set. What we'll talk about today is loss functions and activation functions in this chapter. So what have we seen so far? We have data points, right? And then we can infer model parameters from the data that allow us to estimate things, and then we can do optimization using a loss function, and that couples the prediction of the network with the ground truth, right? And this is what we want to talk about now, what loss functions and what model parameters. And what are best practices to obtain good results. So here's the usual network architecture in a schematic simplification, of course, one input layer, one hidden layer. You might have multiple hidden layers, of course, and an output layer, and that output layer generates a prediction. And each layer has a number of neurons, and the neurons have a number of weights that correspond to these arrows, the incoming arrows. That is basically, each of these is associated with a weight that multiplies the output of the previous layer and aggregates things into each neuron. We've already seen some losses. We've seen L2 loss, L1 loss, things like that, and the cross entropy loss, but we'll look into more details now about what types of loss functions exist. So there is, as I said, the L2 loss, the L1 loss, we've seen it. So in this case, for example, we have a network that in a regression type of challenge predicts a real valued output. And then the loss can, for example, be an L2 loss that says the output f of xi on the input xi should match the ground truth value yi, and then you can impose that the discrepancy should be minimized. And then the question is, how do you measure that discrepancy? You can take an L2 loss, you can take an L1 loss, you can take many different losses. And they will have slightly different consequence. So for example, here, if this is the output of the network, f of xi on the left, this set of numbers, and this is the ground truth values for the respective set of numbers. You can actually think of this in two different ways. You can either have a network that outputs a 16 by 16 array of numbers and has a 16 by 16 array of ground truth values associated with each of these inputs. Or it's a set of, it's just a scalar output, if you will, and you have 16 training samples. And then you would sum over all these training samples. So this is two different interpretations that come out roughly essentially to the same thing, whether it's a 16-dimensional output or it's a 1D output with 16 training samples. And if this is the case, then you can compare the difference between the output and the ground truth and sum it up. And in the L2 error, you would have 12 minus 15, let's say, is 3, squared is 9, etc. And then you get this 33 out in the L2 loss. In the case of an L1 loss, you would get 11 as an output. So clearly the loss functions will be different, but they will both kind of measure the discrepancy in their own way. What are the differences? The L2 loss typically is a sum of squared differences, right? That's what it's also called. This is prone to outliers. So if you have one training label where the prediction is off, then since this enters in a squared manner in the total loss, it will generate a very large loss, right? Whereas in the L1 case, the discrepancy enters linearly into the loss. And as a result, the cost of outliers is not quadratic, but just linear. And so the L1 loss is usually much more robust to outlier. And that could be outliers in your network, that it just doesn't work on one specific sample, but it could well be that maybe the ground truth has an error, right? Maybe there is one label that is just completely wrong, and then you don't want to be too sensitive to that, right? So you might want to revert to L1 losses if you have let's say you have asked 100 experts, and there's one expert who just wasn't an expert and who gave wrong ground truth labels. If you want to be robust to that, you would do an L1 loss, for example. And the L2 loss is popular because it's easy to optimize, right? So it's very compute efficient. Remember, we train these networks by backpropagation learning, and this computes gradients, right? And the best for a quadratic loss is the quadratic loss is just very good for computing gradients, because then you have a linear gradient, right? And there's hardly anything easier than that. So this is often very nice and it's compute efficient. Whereas the L1 loss is a bit more costly to implement. Obviously, you can also compute gradients for that, but this is more compute intense. And L2 loss is good because it gives you smooth gradients, and this is something that is nice for learning for gradient descent. So this is for regression. How do things look like for classification? And by the way, you don't have to choose L2 and L1 loss. There's a lot of other losses, as I mentioned. You could take the norm and then to some power Q, and you could choose Q smaller than 1 to be even more robust to outliers. So there are many things you can do, and people have done. But these are the two most common loss functions in the regression case. For classification, again, we start simple binary classification, and we saw that it's practically the same thing that we have the input. We do a linear combination of the input and sum it up, right, into the score function, and then we do we typically pipe to get the score of the class, we pipe it through some nonlinearity, some sigmoid, for example, right? And we do that to squash the results to a range between 0 and 1, right? Because we want a classification in the binary case. Let's say the ground truth labels are 0, 1. So we want something that generates 0, 1. And what we do is we pipe it through the sigmoidal nonlinearity. And then we can interpret the output as saying, what is the probability that the input xi has the label 1 versus the label 0, right? That's all nice. The question is, how do we generalize this to multiple classes? So this is the idea for two classes. How do we generalize to multiple classes? Here, by the way, this is this. Here is this sigmoidal function, this typical exponential function, right? And then you put in the linear combination of the weights and the ground truth label. For the multiclass, we come to something that is often referred to as softmax. And here's the idea. So rather than having one class, we consider, let's say, C classes. So the label can be a value between 1 and C. What we do is we actually create, a set of score functions, SK, and that is the score for the label for the input being in class K, right? And so this is the idea of the softmax, that we create a score function SK. So we have different score functions with different weights. So we have one set of weights for each class. And then we do a sigmoidal for each class. And then we come up with a probability that, but the question is how we can come up with a probability that that the input xi has the label k. And the key challenge is that much like with dice, you want to make sure that all probabilities summed up over all conceivable classes, that the sum adds up to 1, right? It's much like in a dice. If I throw a dice, I can look at what is the probability that it shows a 1, a 2, a 3, 4, 5, or 6. But obviously, the sum of all these probabilities must add up to 1. Why? Because in total, it must, because it must have one of these instances. It must be among the set. So the total probability summed up over all possible outcomes should be 1. And this is the question, how we can reproduce that here. And it's actually fairly straightforward. And this is the idea, as I said, of the softmax, so that you take the input, you weight it with a set of weights for each class. Theta 1 is the set of weights associated with class 1, here shown in red. Theta 2 is the set of weights that aggregate to the score for class 2, etc. And then you create the softmax. And here is this idea. You just exponentiate the scores, and then you divide by the sum of these three, right? Why do you divide by the sum of the three? Obviously, because it then normalizes it to 1. So if I take these three probabilities and sum them up, in the case of 3 classes here, right, then clearly that sum will be 1, right? It's by construction, and we designed it this way. And so if the score is high for one class, then the probability for that class will be larger than for the other classes. and vice versa. And at the same time, it sums up to 1. And again, why do we use these exponential functions? We'll see a little bit, but one nice feature is that they're very smooth and they work really well for optimization. Because we want to, this is the overarching scheme in learning, is we want to compute losses that are smooth, that are differentiable, so that we can compute gradients via backpropagation learning, and we can train these weights theta I for each class. So if we plug that in here, the score is always the linear combination of the input with the set of weights. So xi and theta I are vectors, right? So this is a dot product here. That is the linear combination of xi with the weights theta I, and then the normalization that assures that all probabilities add up to 1. And this is a technique or a function that is called a softmax. So here it is shown again. We have a set of training data. We have a set of labels from 1 through C. And so we have C classes, and so C sets of parameters, and to generate score functions. So this is, in the previous example, it was 3, but in general, you could have C classes. It's the same idea, obviously. And theta here is always the set of all weights, all parameters of the network. The softmax, as I mentioned, is the default function used for multi-class classification. There are several reasons for that. The first one is, to mention that, I mentioned it, you exponentiate to make sure that the probabilities are larger than 0. So no matter what the linear combination of the weights and the input generates, you want something that is non-negative, right? And you want it to sum up to 1, so you normalize to assure that. So the nice thing, as I mentioned, why do you use the softmax? Well, first of all, you have a numeric stability that is nice. So for example, if your score is offset by a constant, this may well be, right? Then the outcome is the same, right? So if for all classes, the score that comes out is just offset by a constant S max, you can verify for yourself that you get the same softmax output. You can try to prove that yourself. It's not really difficult. It's part of the exponential function has that property, essentially. The other thing that is nice, you can use the cross entropy loss. How does that happen? Well, we saw that before. You can get from a probability to a loss by applying the negative logarithm, right? In a maximum likelihood setting, you would always try to maximize the conditional probability, and you can equivalently maximize its logarithm or minimize its negative logarithm. And that is what we typically call the loss, right? And if you apply the loss here, this is what's called the cross entropy loss. Often people say cross entropy and softmax is the same thing. Strictly speaking, no, in the sense that the cross entropy loss is the negative logarithm of the softmax, but they're related by the negative logarithm. And they are the default for multi-class classification. And so this is the cross entropy loss. And we'll talk about in a second why this softmax is a suitable way to do things and why it is better than at least some other choices in the literature. Here's the idea on an example. How does it actually work? So here's the cross entropy loss applied to 3 training examples and 3 classes: cat, chair, and car. And let's say the scores of these score functions, they're made up here, but let's say if we compute for these 3 classes the scores for each image, then we get these numbers, right? Ideally, what you would like to see is that the score is really high for the image that you're looking at. So the cat score should be high for cat, and the chair score should be high for chair, and the car score should be high for car, but it may not always be like that. So let's say we have these numbers, and then we can look at losses, right? And we can look at what are the losses here. How do we compute them? Very simple. We take, as we saw, the input image, let's say the cat image, right? And we want to compute what is the loss on the cat. So we take the scores, we pipe them through an exponential, right? This is what we see here, exponentiate the scores. Then we get these, and then we normalize, right? That means we take this score, 24.5, after exponentiation, 24.5, and divide by the sum of the 3, right? And then we get here 0.13, 0.87, and 0, 0.00. And then we apply the negative logarithm to get from the softmax to the cross entropy as a loss. And this is the loss we get. So for now, we only care about the cat loss, but that would be the 2.04, right? And this is what we have here. So that would be the loss for the cat. Now, if we do the same for the chair image, we find it's 0.079. And if we do the same, you can do it for yourself for the car image. So you take these 3 scores and pipe them through the same function, and then you get 6.156. And that means the overall loss for this data set would be the loss on the first sample plus the loss on the second plus the loss on the third, and then normalized. And so this would be 2.76 as a loss. And then you can use these losses, you can compute gradients by backpropagation learning and update the weights in order to improve that loss, to make sure it has a small loss on the cat and on the chair and on the car, respectively, right? And this is the case for the cross entropy loss based on this negative logarithm of the softmax function that we just introduced. What I want to show you in the following is why this loss is good for multi-class classification. And good means obviously relative to other choices in the literature. A very popular choice for multi-class classification that was proposed in the support vector machines, for example, that we don't really talk about in this class, but the support vector machines were really popular in the 1990s. And they were the state-of-the-art technique, for example, for classification. When I started my PhD, this was the age of support vector machines. By now, they've been largely superseded by the deep neural networks. But let's look at things in more detail. In the support vector machines, they use this so-called hinge loss. And it's a little bit different from this cross entropy loss. So the aim is also to do multi-class classification. So we have a set of inputs, we have a set of class labels as a ground truth, and we want to train. And what the multi-class SVM loss or hinge loss is doing is, given the scores for each class, it takes the difference of scores plus 1 and then does a maximum of that with 0. The idea is this looks a little bit strange at first glance, but basically what it does is it says if the score is SK, then that so what it does is, sorry, if the ground truth score is SYI, this is the the desired score that you want, right? And what it does is it checks for the discrepancy. And it says it basically checks over all other classes whether the desired class wins out. And more specifically, it measures winning out. It considers it as winning out if the score is at least one higher than the baseline. And if it, you can see that here, if it's at least one higher than the score of the class K, then that loss is zero. So you get zero loss every time the score is at least one higher than all the other scores. So let's say you have a cat image. If the score for cat is at least one higher than the score for dog and for chair, sorry, for car and for chair in this previous example, then you get for example, here in the chair image, the score is more than one higher than the score for cat and for car. So this would, in the case of a hinge loss, incur a zero loss for the chair image. Right? And so as soon as the score is at least one higher than the others, then the hinge loss is happy and it says perfect. And so we can actually compute this hinge loss for the case of this multi-class example with the three images that we had here, cat, chair, car. Here's the score matrix, same score matrix as before, but let's look at what these scores result in as a hinge loss. And here we can see that, for example, the score for, and this is quite easy to compute. There's no exponentiation, nothing, right? So it's very simple to compute. You just take differences of scores. For example, you would take for the cat image, the score is minus 3.2. So you would compare that to the scores for chair and car. On that image, and then you would find this is 5.1 for the chair minus the 3.2 for the cat plus 1, and you maximum over that, and then here the same for the car. And what you find is that in the case of the chair, the chair has a higher score on that image for whatever reason, clearly based on the score, the network thinks this is a chair, right? And that means the hinge loss for that will be high because the score for cat is actually smaller than the score for chair. For the car case, it's fine because the score is much higher. 3.2 is much higher than the minus 1.7 here. So for that, you get a zero hinge loss, right? And so the total hinge loss for this image is 2.9. And similarly, you can show that for the chair image, the hinge loss is zero. Why is the hinge loss zero here? Because the chair score is at least one higher than all the others, and then the overall hinge loss is zero. Whereas for the car, since the score is very small here and actually smaller than all the others, you get a very large hinge loss. And then obviously the total loss is the sum of hinge losses, or the average, sorry, of hinge losses. So L1 plus L2 plus L3 over 3. And that gives you a total hinge loss of 5.3. Now, that only shows how you compute the losses. Why is the cross-entropy loss often favorable over this hinge loss? The hinge loss is easier to compute. Let's be honest, that's a benefit. You don't need to exponentiate anything. You just have sums, right? So that's very fast to compute. And that obviously makes it popular for large learning problems, but it is in many ways worse than the cross-entropy loss when it comes to training. And that is because essentially the hinge loss eventually saturates. As soon as the score is at least one higher than all the other scores, the hinge loss is happy and there is no need for further training, for further boosting the scores, if you will. We'll see that here. So let's say we have three neural networks with three different weights here, model 1, model 2, model 3, and let's say the scores for these models are the ones you see here on the respective, on the three images. So based on the scores, you would say for the first class, it should all three models work well. They M1 is good, M2 is not so good actually. So for the first class, it doesn't work so well. So this is for one image. And then the scores are fairly high for second and third. So this is not, the model 2 is not good for predicting the first class. And M3 is actually the best for predicting the first class. Why? Because it has a high score for class 1 and low scores for classes 2 and 3. Right? So you want to really have a big separation between the different scores. That's what we're aiming. The hinge loss doesn't really reflect that properly, in the sense that the hinge loss, if you apply this hinge loss to these three models for labeling an image from class 1, then you find the hinge loss is 0 for that one, right? Because 5 is larger than -3 and larger than 2 by at least 1, so that gives you a 0 hinge loss. It also gives you a 0 hinge loss for the third model, whereas for the second model, it gives you a hinge loss of 12 because 5 is just not much larger than, it's actually smaller than 10, right? Whereas, and so the hinge loss tells you that model 3 and model 1 are good, but model 2 is not good. So in that sense, it appropriately identifies model 2 as being not suitable, but it cannot really distinguish between models 1 and 3. They're both equally good because once the scores are sufficiently separated, more than one, then the hinge loss is happy and doesn't see need for further score improvement. And this is different with the cross entropy loss. And that's because the cross entropy loss will, I don't know why it's not shown here in the middle, it doesn't really matter. So the cross entropy loss also identifies model 2 as being bad, but it distinguishes between models 1 and model 3 in the sense that model 3 is considered better. And model 3 has a smaller loss now. Why? Because the bigger the discrepancy between the scores for the true model and the false models, for the right class and the wrong classes, the bigger the score discrepancy, the better the cross entropy loss, the smaller the cross entropy loss. And in a way, the cross entropy loss will never get 0, right? Because you have these exponential functions. They will always be non-negative. They will always be non-zero. And so the cross entropy loss will always be able to discriminate the scores. And so whereas the hinge loss doesn't distinguish between models 1 and 3, the cross entropy loss allows you to distinguish, and once you use it for training your weights, it will aim to further and further separate the scores for the different classes. And that's what you really want in a learning regime, that it separates the scores for the right class from the wrong classes. And so, in other words, the cross entropy loss always wants to improve the score discrepancy, whereas the hinge loss only cares about the score discrepancy being at least 1. Now the question is, how do we combine loss functions with weight regularization? How do we optimize parameters of our network according to multiple losses in these compute graphs, right? And this is what it looks like. We've seen compute graphs, right? So here's the input, here's your network parameters, theta, and then you have a regularization loss here and a data loss, and that combined gives you the full loss. And then you want to find optimal weights, theta, and unknowns of the unknowns of your optimization problems. And you want to compute gradients with respect to these weights, theta, and then use backpropagation learning to aggregate these and compute these gradients in the compute graph. The loss in the compute graph looks as follows. So you have score functions, you have data loss, the cost entropy loss in particular, or the hinge loss. And then you have additional losses like the regularization loss, like let's say an L2 loss, for example, or an L1 loss, if you will. And then the full loss, as mentioned, is the data loss plus the regularization loss. So how does that look in an SVM case? So we have a regularization and a hinge loss. Here's an example. So here, so these are two possible regularizers that we consider, an L1 regularizer and an L2. In this case, let's choose the L2 regularizer, so the sum of squares of the weights, and then and in general, you can use different kinds of regularizers. You can also use L2 on some parameters and L1 on other parameters, if you will, or something else, right? And then you can put that into the compute graph, and you can, you can do then backpropagation learning. Here is the example with the SVM loss, but we can also use a cross entropy loss, of course. And so this is what it looks like. So for this input configuration, we have the regularizer is in the L2 regularizer is 1. And for the other set of weights that you can consider, let's say this one, 0.25, 0.25, 0.25, you get a regularizer of 0.25, right? You can do the math. It's, 1/4 squared is 1/16 times 4. So you get you get this out. And so in total, if you have weights W1 and W2, the total regularizer is the sum over all of these. For the weights, let's say, yeah, 1 and 2. Now we want to talk about, so this way you can compute things, you can put things into the compute graph, and then you can do backprop learning to determine the gradient and to then update the weights in a gradient descent, in a stochastic gradient descent, or with momentum, etc., much like we discussed. Let's talk a little bit more about activation functions here. So these nonlinearities that we have in the neural networks. So we've seen that, we get the scores by aggregating the input with a set of weights, and then we pipe these into an activation function. And the question is, what is this activation function? What choices do we have? And typically, traditionally people used since the 80s and 70s and earlier, They were using sigmoidal activation functions. They were sometimes a little bit biologically inspired, one should say. What's nice about them and why people use them is that they are bounded between 0 and 1, so it makes them well suited for classification problems. Additionally, they are very smooth, right? So this is really nice. You can compute gradients, right? So for learning, this is in principle looks like a good idea. And that's why people had been using them a lot for machine learning. But we'll see in a second that the sigmoidal is not actually ideally suited for deep learning. And this may be one of the reasons why it took time for deeper networks to emerge in the sciences, because they don't work well with the sigmoidal activation function. We'll see that in a second. So we can compute gradients. We can even compute them analytically for this exponential function. So that's really nice. But one of the things to observe is that far away from 0, the gradient, so the functions plateau either to 0 for very negative values or to 1 for very positive values. And the gradients in these locations get very small. They converge towards 0, right? And this was a big issue, the issue of zero gradients, or vanishing gradients, as is often called. Because what happens if the gradient of the sigmoid is small, then it affects the overall gradient. Remember, we compute the total gradients by backpropagation, by chain rule in this compute graph, right? And if there is one term in this product of terms that we generate here to aggregate the full gradient, in this chain rule derivative in the backpropagation learning, if there is one term, namely the derivative of the activation function with respect to the weights, if that term is 0, then the whole gradient gets very small or gets near 0, right? And that means then the learning starts to stall. Things don't move because we move with the size of the gradient, right? So that determines things, right? And so the overall gradient will then start to vanish, will start to disappear in this regime. And people often say that the neurons are then saturated. So the input to the neuron is too large, and then that kills the entire gradient in that location, and the gradient flow is kind of blocked, and then the learning doesn't advance. And this is what happens in neural network training, in particular when you have very deep networks. Then there will always be layers or neurons along the way that saturate and essentially die out, if you will, right? And this is true if the input to a neuron is very large, but it's also true if the input to the neuron is very small, right? If same thing, right? And then the backpropagation learning doesn't work. And so it only works in this regime near 0 where you have a reasonable gradient. And this regime is called the active region of the neuron. That's where the sigmoidal neuron is active, but otherwise the neurons die out, they saturate, and then you have what's called vanishing gradients. And so for large networks with many layers, it's practically not possible. People couldn't get these to work because they were using sigmoidal activation functions that saturate that plateau, right? Another issue is that the output of each neuron is always positive, right? Because of the sigmoidal. So the input for the next layer is always non-negative. It's always positive. And so one can ask, what is the disadvantage of this? And the issue is that in backpropagation learning, we propagate the gradient through the compute graph. If the inputs to the next layer are always positive, and then something strange happens. And then if you, let's say you have, let's assume we have positive data that comes into the network because of the sigmoidal activation function. Then we sum this up, and then we compute the gradients. Then what happens is if the sigmoidal, if both the x are positive, x1 and x2, because of a sigmoidal activation in the previous layer, then the gradients point in, and then you have these derivatives of the activation function. They're either positive or negative, but they're the same, right? And so as a result, everything is the gradient, the components of the gradient are both either going to be positive or both going to be negative. And so the allowed gradient, if you have two sets of weights, W1 and W2, or two weights, W1 and W2, then the gradient vector with respect to these two weights is either always positive or always negative. And so if your minimum that you're looking for is actually in the bottom right corner of your weight graph right here, then you cannot take steps in that direction because the gradient with a sigmoidal function doesn't allow such steps. And what it will generate will be at best steps that zigzag like you see here in red to ultimately find the desired minimum, and that is not ideal. So the gradients as a vector over the different weights, they cannot be in any direction, but they can only go in certain directions. And this phenomenon comes from the fact that that the output of each layer undergoing a sigmoidal activation is always non-negative. And so you want to somehow get into a regime where the output of each neuron is actually zero-centered, not just for the input data, but for each layer. And so you would want to move to an activation function for that reason, that is the tangent hyperbolic, for example, and this was then used. The nice thing of that is it is zero-centered almost by construction, if you will, and it allows arbitrary gradient vectors in arbitrary directions in your weight space. But the issue with this 10H activation, obviously you can see it here, is it still saturates for very large and very small values, both for large and actually for small. But so this tangent hyperbolic replaced the sigmoidal to some extent at the end of the 1990s. People started using 10H as an activation function. Based on papers, for example, like this one by Jan LeCun from 1991. But one issue remained the saturation, and that also limited the capacity of these networks to be trained for very deep networks. With more layers, you would get vanishing gradients, and then the learning would stall at some point, and they wouldn't converge to the desired solutions that you would need for powerful machine learning. And this is why another activation function became popular. It was propelled by this work by Alex Krzyzewski and collaborators that achieved very good performance on this well-known ImageNet data set. And this is the rectified linear unit that we've already talked about. It's a very simple function, and by construction, it doesn't saturate in the sense that it is just for positive values, it's just identity, so x, but it is a nonlinearity in a way that for negative values, you truncate to 0. So this max 0x. And the nice thing of that is it provides fast convergence. It doesn't saturate, so you don't have the same issue with vanishing gradients. And it gives you large and consistent gradients throughout the entire regime of positive values. Question is obviously what happens if the ReLU outputs 0. So if you're in the negative regime, then the gradient is 0, obviously, of the ReLU. Then you have a vanishing gradient, and that is often called the dead ReLU. If if the input is negative to the ReLU, then nothing happens, and then it doesn't learn. And so that's why sometimes people reverted to variations like leaky ReLUs. We'll come to that. A bit more on rectified linear units. So what you do in practice to avoid dead ReLUs is that you provide slightly positive biases, some B, something like 0.01. That makes it more likely that the ReLU stays active and the neuron stays active and doesn't die off. Or, as I mentioned, that you introduce what's called a leaky ReLU. This is one that always has gradients. The gradients are never exactly 0, right? The gradients are just larger in the positive regime and smaller in the negative regime. So this is nice. It means the leaky ReLU will not become 0. As a result, nowadays, most state-of-the-art neural networks as an activation function use either the ReLU or a leaky ReLU. But it is still okay. In some layers, especially the last layer, you might still want to use a 10H or a sigmoidal activation function. But throughout the middle layers of the network, you would want to go with ReLUs or leaky ReLUs just to avoid vanishing gradients. So, for example, generative adversarial networks often use leaky ReLUs, but also larger convnets sometimes use leaky ReLUs because they do not die, like in the standard ReLU. Then there is the parametric ReLU, right? So that is a ReLU where you learn the slope as well, but so you have a parameter alpha that you learn, but it increases the number of parameters that you need to train. And basically that brings the trade-off, the question being, how many layers do you want to have in your network, and how complex an activation function do you want to have? And nowadays, I often see that people prefer using, more layers and simple activation functions over fewer layers and more powerful activation functions. But, people have tried different things. So this one also doesn't die, but you have another parameter. An even more sophisticated approach is called max-out units. This is discussed in a paper by Ian Goodfellow, 2013, ICML. Here you see the idea. Basically, you have two sets of weights, W1 and W2, and biases B1 and B2. And then rather than taking the maximum between one set of weights and 0, you take the maximum between these two sets of weights. And you can do that obviously for 2, 3, 4, 5, 6 sets of weights once you're at it, But it means in one layer you double, triple, and quadruple the number of parameters, right? So there is a massive trade-off that you're bringing in here. The way you can visualize these max-out units is very nicely. For example, the rectified linear is what you see on the left, right? And then, sorry, this is, yeah. And then basically each set of weights is a linear function. And then if you take a maximum of 2 linear functions, then you get this function in the middle, for example. And if you take the maximum of n linear functions, you can really approximate any convex function, right? So if we have this parabola here, for example, you can see how it can be well approximated by saying take the maximum of n linear functions. And that will, by construction, give you a convex set, convex function. So in a way, you get a piecewise linear approximation of a convex function. And the number of pieces relates to the number of sets of weights that you have in your max out unit. The nice thing is this generalizes rectified linear units. It's still a linear regime. In every domain, you have something linear. In every stretch, basically. They don't die, so the gradients don't become zero typically, but and it also doesn't saturate. But there is a trade-off because obviously the number of additional parameters increases massively, and so these max out units are being used, but to my knowledge, people still predominantly prefer more layers with simple ReLU or leaky ReLUs because of the massive increase in the number of parameters here. So in a nutshell, there are different activation functions. Here are some that I plotted. I didn't mention all of these. The swish function, for example, is another possibility, a function that where actually it curves back up again in the negative regime, as you see here. But these are all conceivable functions. What's important, if you use them in your neural network, you have to distinguish different regimes. You have to keep track of what is the range of each function. If you have a linear function, it has a range from -infinity to infinity. Step functions have just 0, 1 as output. Sigmoidals are in the range between 0, 1, but will never get 0, never fully 1 either. Then you have the 10H function that goes from -1 to 1, etc. Why is it important to keep in mind the regime, the range of each of these activation functions? It's because you have to construct your network architectures appropriately to make sure that the next layer can knows what the range of the input is. A quick guide, sigmoids and 10H are not really used much in feed-forward networks, possibly for the final layer, but not in the intermediate layers. The ReLU is the standard choice, or the leaky ReLU. The second choice are variance, leaky or parametric ReLU, or max out, then as a more sophisticated generalization of a parametric ReLU. Typically, recurrent networks will require a sigmoid or 10H or something similar. And in summary, it's important to understand the range of each of these. The next part is weight initialization, but we'll do that in person next week. Thank you very much.